So we will have the test on Friday. I'll send a message just a reminder. Here. Alright. The exceeding chart of the door. It's going to cover all of chapter 0 and all of chapter 1. Prepare to look at the old exam. So please note that chapter 0 I didn't start doing that until last semester. It was sort of still here. But look at the homework here. That'll give you a good indication of what to expect. Like I said, you need to know what the shell theorem is, Newton's shell theorem. We'll spend a little bit of time at the end sort of going over that, actually. But go through your notes on chapter 0. You could see some short answer things for the chapter 0, just to describe certain laws that we talked about, Gauss's law and the shell theorem. Let's finish up chapter 1. Let's try this. You'll see some questions in the multiple choice, maybe in the free response. I haven't made your test up yet, but you'll see questions in the multiple choice about electric fields for just interpreting electric fields. Remember those rules that we had that we went over last time? The rules are that your electric fields come out of a positive charge, they go into a negative charge, and the number of field lines represents the magnitude of the charge. So a charge with twice the number of field lines of another charge will have twice the charge of that other charge. So let's try this one. This one, the charge on the left here has a magnitude of 6 microcoulombs, so either plus or minus 6 microcoulombs. What is the charge on the right? Let me pull up your clicker base. I'm sorry. I'm not quite all here this morning. I'm very sorry. What is the sign and magnitude of the right charge, the charge on the right? Ask your neighbor if you're not sure. Most of you have the right answer. Just a couple do not. I'll stop at 22, 23. Okay, awesome. B is the right answer. Remember our rules that they come out of a positive charge, they go into a negative charge. So I know this one. Hold on just a second. I'm sorry. This one is positive, this one is negative. This one, I tell you, is negative 6 microcoulombs, or 1, 2, 3, 4, 5, 6 field lines over here. There are 6 plus 7, 8, 9, 10, 11, 12 field lines over here. So this one's going to have twice the charge. It's going to be plus 12 microcoulombs. So we put B, yeah. All right. We'll see another one like that. I think that might have been the end of this chapter. Yeah. We still have some clicker questions though for this. Oh, this is chapter 2. I think that's right. Is that right? We still have clicker questions? Where? 1.11. Thank you, Ashley. I'll post the concept test this morning. Okay. So in a uniform electric field, an empty space, a 4 coulomb charge is placed, and it feels a force in this electric field of 12 newtons. If the charge is removed and then a 6 coulomb charge is placed at that point, what force will it feel? All right, let's stop at 45. 45. Okay, E is right. A couple ways you can think about this. You're increasing the charge from 4 coulombs to 6 coulombs. That means you're increasing it by a factor of 1.5. Right, 4 times 1.5 is 6. You've increased it by 50%. That means that your force is also going to increase by the same factor. Because remember, my force is equal to Q times E. So if I'm increasing my charge by a factor of 1.5, as I am here, 4 times 1.5 is 6. That also means I'm increasing my force by 1.5. That's probably the easiest way to do that, and I recommend that. But you know, if you want to go through sort of the whole process, you could say, well, with a 4 coulomb charge, I get a force of 12 newtons. So what is my electric field? Well, this electric field is 3 newtons per coulomb, or 3 volts per meter. I'm sorry, 3 newtons per coulomb. So our force then for the 6 coulomb charge will be 6 coulombs times 3 newtons per coulomb, which is 18 newtons. Either way you want to go through that, you get to the same answer of 18 newtons. It's a linear relationship. F is equal to Q times E. So any increase by Q or E will increase F by the same amount. All right, what are the signs of the electric charges here? The field lines are traveling in this direction. All right, let's stop at 30. Okay, good. B is the right answer. Field lines go into a negative charge, and they come out of a positive charge, so it looks like that. All right. Is it cold in here? Y'all feel cold? It's hot. We to open the door? Y'all be sort of okay? Okay. Sometimes if I get cold in here, like I'll move over to the corner, because the corner is always warmer than the rest of the room. Y'all know that? It's always 90 degrees. All right, which charge has the greater magnitude here? The green one or the red one? All right, I'll stop at 18 or 20. Say 20. Okay, good. B is the right answer. But that one was so easy. No joke for that one. I'm sorry. Because that last joke, that was a good joke. Like you're going to be telling your friends that one. So I think that counts for 2. Okay. And the ratio, we've already seen it. It's a 2-to-1 ratio. Logan? No, that doesn't matter. The arrows just show the direction. Sorry for that. The arrows just show the direction of the lines. Y'all already asked if it matters about the number of arrows on the line. Now you're just looking at the direction of the lines and then the number of field lines. All right, that's the end of that. Let's see. Also, I did not send y'all a message about the derivation, but what I want y'all to do I want you to do the charge disk derivation. It's in your homework. It's really just an exercise, but I also want you to write an explanation for that as well, a paragraph describing how to derive, what are the steps in your words, not the charge disk. The electric field for a charge disk at a point B. I'll send you all print out that I'd like you to do the derivation on, that you can sheet with the figure and stuff on it. You can print that out and write your derivation on there, along with a paragraph describing it. Okay? Should be an easy 10 points. Just sort of go through the motions of that, but I do want to see a paragraph describing in your own words how you do that derivation. Not a whole paper, but 4 to 6 sentences for each step, or not for each step, maybe a sentence for each step, and there are 4 or 5 steps. Alrighty. I'm pretty sure that's on the homework video. Somebody confirm that? Have y'all seen the homework video? Yeah. And I will send you this figure so you can just turn that in. Please do turn that in at the beginning of the exam. That way I can go and start grading them while y'all taking the exam. All right. You have particular questions about the exam coming up? Let me just give you a little primer on what to expect. We've had just 2 chapters. It's going to be a normal length exam, but not a whole lot of material. You have the universal law of gravitation. Or you can think of this, our Coulomb's law. That's when I have a configuration of charges and I need to find the force on one of those charges, something like this. I want to find the net force, 2D vectors, or electric fields. So you'll have a 2D vector problem that will either be universal law of gravitation, Coulomb's law, or electric fields. Those are all the same problems. The only difference will be, how do you calculate the magnitude of the force or the E field. Remember, you will have an equation sheet. That equation sheet is on the website, so I recommend that you print it out and just are familiar with what's on there, especially with the constants. Make sure that you see which constants are available on there. That way, when you encounter a problem that says, oh, a proton or whatever, and you know where to look for the mass and the charge of the proton. Or but there are other constants on there as well. As I said, you need to be aware of what is the shell theorem and just be able to describe it in your own words in a sentence or two. Remember the shell theorem, Newton proved this by showing that the force on a point mass due to a shell of mass is the same as the force due to a point mass. And he did this by integrating over that shell and showing that the force due to that shell is the same as that given by this universal law of gravitation, which usually only applies to point masses. You need to know about gravitation. Gravitation near the Earth's surface. We spent some time on this. That was this whole thing looking for the acceleration due to gravity is gm over r squared. The gravitation near Earth's surface. I think there's homework on today. So we skip inside Earth's surface. Also gravitational potential energy. That was that U is Gmm over R. You have a homework problem like this where you have a configuration of 3 particles, mass particles, and if you want to find the total energy that's contained within that configuration, then you calculate the potential energy due to each separate pair of masses and then add those up, and that gives you the total amount of potential energy that's contained within that system of particles. Unfortunately, we didn't get to chapter 2 because we have an almost identical problem with electric charges. So you'll see that again in the next test, but it should be easy by then. Let's see. Also, escape speed. We did see escape speed. I don't remember if that's in your equation sheet. Let me just take a quick look. Your equation sheet is here. Okay, yeah, it looks like that equation is there for escape speed. But also remember, escape speed is based on this idea I might ask you this in a short answer. Escape speed is based on the idea that the gravitational potential energy plus the kinetic energy, that these remain constant. These, when we add these up, they remain equal to 0. So if I have an object on the surface of the Earth, a rocket ship or whatever, if I have a rocket ship on the surface of the Earth, its total potential energy is 0, And so as it goes along, the total potential energy has to always equal to 0. So remember, we did this derivation. It's negative gmm over r plus 1/2 mv squared. That's equal to 0. And when we solve for v, then that gives us the speed that's needed for that rocket to escape the Earth's gravitational field. I need to do derivations on the test, but you should know that that's where that comes from. It's stuff that we've seen, and it's applied to the gravitational potential energy. All right, let's see, we didn't do Kepler's particles. And then finally was Gauss's law. We're going to see Gauss's law in the next chapter in a little bit more detail, but for now, you need to know what Gauss's law is. Remember, Gauss's law said that the flux, but you also need to know what flux is, of course, is equal to negative 4 pi g, or that's that gravitational constant, it's on your equation sheet, times the mass inside your surface. And we talked about those Gaussian surfaces and what they are. For 3 different objects, you should be able to describe how Gauss's law is applied for the sphere, the cylinder, and the flat. Think again that those equations are on. No, they are not. But you should go back over the derivations for the gravitational field G. Remember, this is gravitational field for a sphere. Remember, that was that G is equal to gm over r squared. Because that also applies for the Earth. So you need to know it for a sphere, and then other exotic masses, like if you have a mass of a cylinder. And we found with that G was equal to negative 2gm over Lr. I wouldn't even really call it a derivation, but yes, you do need to know how to apply Gauss's law in those 3 scenarios for a sphere, a cylinder, and a flat sheet. Okay? Let me remind you that Gauss's law, you need to calculate the flux, and then you just set it equal to this negative 4 pi g mass inside. So the flux, you remember, or you might not remember, but our flux is this phi, and it's equal to the gravitational field times the area. All right, so for each of these, you would just say G times the area is equal to negative 4 pi G times the mass inside your Gaussian surface. And so, for example, with your sphere, you use a Gaussian surface that is a sphere. With your cylinder, you use a Gaussian surface that is a cylinder. And with your flat sheets, you use flat sheets for your Gaussian surface. So you have a flat sheet here, and you put a surface on top and a surface on bottom. These are imaginary surfaces in which we imagine what is the gravitational field that's going through this area. Again, we're going to come back to this after the break, when we'll look at it with electric fields and go into a little more depth. But for now, all you need to know is that this flux is equal to my gravitational field, or we've been calling it the gravitational acceleration, but it is really the force per unit mass, or the gravitational field, times the area. So yes, you do need to know how to apply that for the sphere, the cylinder, and the sheet. Okay? I think that actually part of it is done for you, because the hard part for some of you is just remembering what those areas are, and they're right here. The area of a sphere, the area of a cylinder, and the area of a square. Though remember, with the cylinder, if you go back and look in your notes, we leave off this 2 pi r squared because we imagine a cylinder that's really, really long, and we just, so the end pieces don't really count. The area is overwhelmed or is dominated by the area of the circular surface. Okay? It's important for you to get that now, because we'll see it again later. So you can, I can't guarantee it's going to be on the test, but I'm fairly certain that it will be on the test. Okay? Is that clear? I'll prepare you. Y'all could do that. Y'all could do it right now, right? If I gave you Gauss's law, as I do right here, and the area of those 3 surfaces. Yes. Yes, you could do it. All right, so you will see that, most likely. Pretty certain that you'll see it. And then that's it for Chapter 0. Chapter 1, you have sort of the basics of charge. The basics of charge, those things are probably going to be in multiple choice. You'll see a few questions about just the nature of charge. Positive charges or like charges repel, opposites attract, sort of charge by induction, charge by conduction. Just go through your notes on that. Look at the concept test. There are some questions like that. I think that most of you will probably get those correct. You sort of have to reason out how charges behave when they're around other charges. Remember that fact that charge is quantized, charges can move around on conductors, that sort of thing. And then Coulomb's law. And as I said, with Coulomb's law, where you have to find the force due to multiple charges, that question, which will be a free response question, will be one of these three. It'll either be masses together, Coulomb's law, or an electric field, a 2D vector problem, which you'll certainly have. All right. So make sure that you can add vectors in 2 dimensions and that you can do it well. I'll try to make it as easy as possible just so that you can demonstrate that you know the process without getting bogged down in a lot of numbers. So 2D vectors, you could see some qualitative things as well, like where I give you a configuration of charges and you just have to trace out the vectors that are acting on those charges and not give a numerical answer, but just say, yeah, if I give you a range of answers, you could say, what is, this would be the force, for example. We had some questions like that on one of the quick tests. Electric fields, again, might have to do a 2D vector problem with electric fields. You could also maybe have to do, how does a charge respond in an electric field? If you look back at the homework and some of the quick tests, we have some questions that are similar. And this will be using things like our force, which is equal to Q times E, right? So if I have a charge in an electric field, it feels a force. Don't forget your Newton's second law. Our A would be F over M if I found the acceleration. And then we had a couple of kinematics equations you'll still need to know. V is equal to AT, and X is equal to 1/2 AT squared. Those aren't on your equation sheet. These 3 things are not on your equation sheet, so you just need to, if you haven't memorized those, you need to know them. Notice I've left off the V naught because, you know, in practice, the things usually start at rest when we're dealing with these type of questions. Okay? All right. You have the derivation, which you'll do in the next couple of days and bring in on Friday morning. That'll be for the ring of, the disk, the charged disk. Solutions online. I just want you to show me the solution and then think about, you know, each step as you go through and write out in your own words how to derive that. I don't want a book, but I don't want 3 words either. Maybe shoot for, if you do 5 sentences, 50 to 100 words. And then electric field lines, and that's it. You might have that as a free response, but if you have it as a free response, it'll be, you know, like I'll give you a configuration of charge, and I ask you to draw the field line. So for example, if I gave you a dipole, say I gave you a dipole that looked like this was plus 2Q, and this was plus Q, then you would draw the field lines like this. You would draw field lines here, here, and maybe here, and then you draw 6 field lines. Like that. Or if this was a negative Q, then your field lines would look like this. You'd have 2 going there, and then you'd have 2 additional ones there. Just looking that the directions are correct. Notice your arrows made this negative, and that's why the arrows now go into that negative charge. And then also that you have the proper ratio. You don't have to try 100 field lines, just make sure that you get, in this case, a 2-to-1 ratio. Okay? Could be a free response, could be multiple choice, but testing it that you understand what the field lines map out. All right? I don't think we're doing field lines in the next chapter. I think we stop off here. But we do still talk about fields. Yeah, we do see some field lines in the next chapter. Alrighty? Any questions about what to expect? That's the exam. I mean, I've already told you some of the stuff, the derivation, the 2D vectors, a short answer, probably either Shell theorem or Gauss's law. Probably can have that derivation, basically call it, but I don't really call it derivation. It's more of an application of Gauss's law. I might even give you some numbers to figure out, what is the gravitational field, say a certain distance above a sheet. That way, if you ever run into a supermassive structure that's sheet-like in the universe, then you can calculate the gravitational field. That's pretty useful, actually, when you think about it. Okay? It is actually fairly useful. I mean, maybe not for y'all, but some of you might be, if you look at things that are really big like that have their own gravitational field. I guess that would really just be astronomers. Probably none of y'all are ever going to be astronomers. Well, some of you. Huh? Okay. Any questions, Joe? I'm going to move on to the next chapter, but if you have questions or areas that you're concerned about, we can spend more time on it. But we have 25 minutes, 30 minutes left. Can I do one and not do the numbers, but sort of go through each of the steps? Okay. They get sort of tedious. I'll make up one that's a little bit easier. Is that okay? All right. So let's imagine. Let's do an electric field problem. Okay. They all work out basically the same. It's just how are you calculating your magnitudes? Are you using universal law of gravitation? Are you using Coulomb's law? Or are you using that E equals KQ over R squared? So let's imagine that I have two charges. A charge here, 50 nanocoulombs. No, not 50, let me see. Let's say we have 25 nanocoulombs. Nanocoulombs, and let's say I want to know a point up here. I want to know what is the electric field at this point, and then I say these distances are 4 meters and 3 meters. All right. First of all, I want to draw my vectors. I say that the 9 nanocoulomb force or electric field is here. I'll call this E1, and the other electric field is in this direction. I'll call that E2. The next thing you want to do is figure out the angles. You need to recognize that this is a right triangle. It's a special right triangle. It's a 3, 4, 5. So this angle is 37 degrees. Okay. This angle is 53 degrees. And so I need to figure out now what is this angle right here. And if I think about it, if you look at sort of how your angles are laid out, we draw these two lines here. This angle will equal this angle, so it'll be 53 degrees. That means this angle will be 37 degrees. Okay, so you need to go through that geometry and the trig, the right angle trigonometry, to figure out the direction of your vector. Then if I draw my vectors, I find the x and y components. E1, E2, sine of 37, because I've now found that direction, and this is E2 cosine of 37. All right. Now you would find the magnitudes, or you might have already found the magnitudes. I'm not going to do that here, but it's going to be E is equal to KQ over R squared. Do know that I try to give you numbers that are easy so that you're not dealing with a whole bunch of decimal numbers. So I try to give you nice round numbers. Not always, but I try to just make math a little easier. So look for those things that cancel out. Like for example here, notice I have a 9 nanocoulomb charge, so it's going to be K 9 times 10 to the 9 times 9 times 10 to the minus 9, so those plus minus 9 will cancel, divided by R squared, which is going to be 3 squared, which is 9. So that electric field would just be 9 newtons per coulomb. Okay, so just look for those things that cancel out to make your math a little easier. Now, I can combine these vectors. I'll call this EY, and I'll call this EX. After you find those magnitudes of E1 and E2, those will have numbers, whatever they happen to be. I also have to add up those two vectors in the y direction because they're in the same direction. If they were in opposite directions, I'd take the difference in them. Now I recognize that I have EX, EY. I want to find the magnitude and direction of this vector. That'll be my final answer. To find that, the magnitude will be the square root of EX squared plus EY squared. And the angle, here I'll call this phi, will be the inverse tan. Opposite over adjacent. And then that would be your answer. In this case, the angle would be so many degrees, whatever that is, at some above the positive x-axis. It'll be along that level of difficulty. I'm not saying it'll be that exact problem, but there are ways to make these problems simpler with symmetry, so that forces cancel out, or so you only have one vector that's off axis. Does that help a little bit? Yeah. I'll go through the homework. There's several examples here. I'll look at those as well. Alrighty. What else, y'all? Anything else? Teaching you? On to the next chapter. I know that's not real popular, but that's okay. Not really popular. But let's move on to the next chapter. We have some good time left. Next chapter is a continuation about Gauss's law. Give me just a second to sort of see what I have here. Pretty short chapter. So you'll probably just have one, maybe two questions on the next test about this. By the way, this first test is so little material. I sort of front-loaded the test this semester to see how that works. Later, when we ask for comments about the course, you can tell me if that's good. But I think it'll be good to sort of have a test with not much material on it, because y'all are just first getting into the routine of things, and it also sort of puts us off schedule with other professors, because you don't have many exams this week, right? Yeah. Because people are lazy. They don't want to write an exam before Mardi Gras. Wait, did I just say that? No, because I'm lazy. Oh, wait, no, that's not cute. I'm sorry. Okay. Sorry, y'all, give me just a second. I didn't think we'd get this far today. Okay, so Gauss's law gives the relation between the electric field at points on a closed Gaussian surface to the net charge enclosed by that surface. Now, we've seen Gauss's law already with the gravitational fields, and that was, we've seen it written like this, that the flux is equal to negative 4 pi g times the mass enclosed, the mass inside that Gaussian surface. This is written for a gravitational field, but electric fields are basically the same as gravitational fields, so we'll see a similar thing for Gauss's law related to electric fields. So it's really just a law that relates to field lines, but we'll now relate it not to gravitational fields, but to electric fields. We're going to define a Gaussian surface. We've already used Gaussian surfaces, but let's just sort of humor me. it's an imaginary three-dimensional surface or shape that, that encloses a distribution of charge. Often it's useful to make these surfaces very regular, like we make it into a sphere or we make it into a cylinder or whatever. But we don't always have to make it a regular surface, and I'll show you an example of that. But often the shape mimics the shape of the charge distribution. But we'll see some problems where we're just sort of thinking about the flux and thinking about Gauss's law, where we just make up some funky surface. And you can certainly do that, but often we'll let it mimic the shape of the charge distribution. All right, now flux. You can imagine flux as the rate of flow through an area. So let's imagine that we have this flow, like we have airflow, for example. We have airflow, air is traveling along these lines in a straight laminar fashion so that it's not all twisty and curvy, but we just have airflow or some other liquid that is flowing, imagine it as airflow, going through space. And then we put in a surface. So we imagine that that airflow is going through some square or whatever. It's going through some area. So this is just some area that you're imagining that the air is flowing through there. So we imagine then that all of the air is flowing through this surface. However, what would happen if, in this case, the area is perpendicular to the flow? What would happen if instead the air was going perpendicular, or excuse me, was going parallel to the flow? How much air would actually travel through that imaginary area that I have? It's going parallel instead of perpendicular. How much air would go through? All of it? Not as much of it? None of it? None. Right. So if I have the airflow going along the same direction as this, say, imaginary area that I have, this metal frame, if you want to think of it as that, then none of the air would actually travel through the area. So if the air flows parallel to the surface, no air will go through the surface. So you might already imagine sort of what we're getting at is that only if I have air that's going at some angle to the surface, that some of it will go through the surface and some of it won't. Right, somewhere in between, not either perpendicular or parallel, but I have a certain portion, say this is my area, and my airflow goes at an angle, say at an angle theta, then the flux, which remember is the amount of air going through the surface, will be something that looks like this. Our flux phi will be V times our area, but I'm missing something. What do I need to put here to represent that I'm only looking for the portion of the air that's traveling perpendicular to this surface? I need to put in my cosine, right. So V cosine theta times the area. So this is a more general term for the flux that we didn't have before. And here I'm talking where V is like my field lines, but we'll see that like when we get to seeing Gauss's law for electric field lines that we'll use our electric field. We'll just replace V now with the electric field. All right. We can also express the area as a vector. Hold on, let me stay on this page. We can express the area as a vector. So our area then will equal to the magnitude of the area times a vector. I'm going to call it n. N is a unit vector that's going to be perpendicular to the surface. So if you imagine our area, it has a magnitude. Our area is so many square meters, but I'm really only looking for a vector that's in a direction perpendicular to my surface. So it's sort of just something that I'm constructing, but it's something that'll be useful when I'm looking for the flux, because the flux, I'm only concerned with a direction that's perpendicular to the surface. Right. Here, n is a unit vector. Unit vectors like I, j, and k, they have a magnitude of 1. So a unit vector whose magnitude is equal to 1 in the direction perpendicular to the surface. So we can then come back to this and have even a more general expression for our flux phi. And you might have already sort of come to this in your mind, because this might look familiar to you. I have one vector, the magnitude of one vector, times the magnitude of another vector, times the cosine of the theta, the angle between them. What is that? Not a cross product, no, but you're close. So the cross product was sine theta term. What is it? It's the dot product. It's our scalar product. So this is going to be our definition for our flux, which is a scalar quantity, is going to equal to V dot A. So this is even the more general term for our flux. It is equal to the first vector, which is our field. Right now we're calling it V, but when we get later into electric fields, we'll call it E, dotted with the area. But it's not just the area, it's the area vector, which is the magnitude of the area times the unit vector, which is perpendicular to the surface. So that way, we're only looking for this component of the field vector, or in this case, the area, that is perpendicular to that area vector. Okay? Now let's look at the flux of an electric field, and all this will come into play. So, the flux of an electric field will be the sum of the electric field dotted with the area vector. And remember, with the electric field, unlike with the gravitational field, this flux can be positive, negative, or zero. With a gravitational field, if we had an object with mass, the gravitational field was always, actually not, never mind. The gravitational field was always positive. We think of negative, but the gravitational field was always positive. Okay? There was always, the flux was always going in the same direction. But with electric fields, depending upon the nature of your charge, the flux can either be positive, negative, or as we'll see, it can also be zero. Okay, just a couple more minutes. Let me define this, then we'll take off, okay? I know you're all ready to go, aren't you? Are y'all just going to stop right here? I don't care what you want. I'm gonna do this. Okay? I shouldn't have even asked. I'm sorry. So our flux then, this sum. Anytime you see a sum, what should go off? What kind of alarm bells? A sum is a what? It's an addition, right? I'm adding up things. It's a what there? In calculus, what is a sum? It's an integral. So we're going to do an integral over this surface in order to figure out what is the total flux. So my total flux will be the integral of E dot dA. It's a particular type of integral. you may or may not have seen this. I'm going to put a little circle right here. This is a surface integral. Some of you have seen this. We've done this actually. We did this last semester with our moments of inertia. But a surface integral just integrates over a surface. It adds up all the components over a particular surface. So we integrate over the surface. So for example, let's say that I have a cylinder that looks like this. Let's say that there is an electric field that is traveling in this direction. I have an electric field that is in that direction. It's a regular electric field. It also travels out here. It's all through this surface. So I have this electric field, and then I say, boom, I'm going to put in a cylindrical Gaussian surface here. And I want to know what is the charge inside this cylindrical surface. And I want to know what is the flux. And then next time we'll get into Gauss's law and we'll see how that helps us. Okay, so I can imagine our flux. At each point, I have an electric field vector. So right here, my electric field vector is in that direction. What is the direction of my area vector in this case? It points straight up. The area vector is always perpendicular to the surface. So my area vector is in that direction. The area vector at that point does have a particular value, but really all I'm worried about now is the direction of the area vector. Over here, I have my electric field in this direction, and then my area vector is also in that direction, because the area vector is always perpendicular to the surface. The area vector is always perpendicular to the surface. Oh, actually, I'm sorry. That wasn't ridiculous. Here, my area vector, my electric field vector, my area vector, to be perpendicular to the surface is going to be in this direction. And then over here, my electric field is in this direction, and my area vector is in this direction. Now, I can calculate then what is the integral of E dot dA for each of these. Up here, what is going to be the integral of E dot dA? I have these two perpendicular vectors. What is the dot product of those two vectors? Now remember, our dot product, just to remind you, I know this is new to some of you, but our dot product, I take two vectors. The magnitude of that, or that dot product, is equal to AB cosine theta. And remember, it just takes two vectors, and it says the magnitude of one vector times the component of the other vector that's in the same direction, and then that will give me the dot product. We used it with work before, because we had work was the dot product of F and D, and the only way to do work was to have a force in the same direction as the displacement. But when I have a displacement that's 90 degrees to the force, what was our work? Zero. It was zero. And that's borne out in the dot product. That when I have two vectors that are perpendicular, like when I have a force in this direction and a displacement in that direction, then I have no work. In this case, what is the integral of this dot product, E dot dA? What is E dot dA here? Zero. This is zero, because E is in this direction, A is in this direction, and so that's going to add up to equal 0. Because I have two perpendicular vectors, the angle would be 90 degrees if you want to think about it in that way, and so that's going to be 0. Now we can consider these other two, like this one right here, the integral of E dot dA. Will that vector, or will that dot product go to 0? Remember, the result of a dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. What's the cosine of the angle between these two vectors? 1. It's equal to 1. That angle is 0 degrees, and the cosine of 0 is 1. So this vector, or this dot product rather, will be the magnitude of this vector times the differential element of my area vector, which is going to be A, times the cosine of 1. So the way this would work out, it would be the integral, these should be vectors here, the integral of e, I'm just going to take e out because it's unchanging, times dA, times cosine of 0. But cosine of 0 is just equal to 1. What's that? You don't even need to add it, right. So what is the result of this? This is just e times a. Because the integral of dA, it is the area. Okay, so that is EA, and now we're almost done. We need to do this portion over here. It's going to be the integral of E dot dA. But this one's different because I have an electric field that's in this direction. My area vector is in the opposite direction. What are the angles? The angle between these two vectors? They're 180 degrees apart. What is the cosine of 180? -1. Anytime I take the dot product of two opposing vectors, it's going to be the negative of what it would be if they were in the same direction. We saw that would work, right? If I had force in one direction, displacement in the other direction, I do a negative work. It's the same here. That's borne out from the dot product. So here, you can probably tell me right off, what is this answer? It's going to be negative EA. So this is a pretty simple surface, but if I want to know the net flux, I add up all of these. So here, with E dot dA was 0. Here, it's equal to positive EA. And over here, it's equal to negative EA. So if I want to know the net flux through the surface, it's going to be what? 0. And you can sort of see the number of lines, the number of field lines that go into the surface are equal to the number of field lines that go out of the surface, the Gaussian surface. But by breaking it into the three parts, we can show that the sum of all of those is equal to 0. So the total flux, C, is going to be 0 plus EA plus negative EA, and that's equal to 0. Right? That probably doesn't make a whole lot of sense to you right now. We'll do some more problems after the break, but I have this exam out of the way. Y'all do great on it, I'm sure, and we'll come back after the break and see how some problems go. All right. I'll be out this morning for just a little bit, about 9:30, but I'll be around. I'll try to be a little running to come to me or whatever. You can come to the office hours or come, just drop in or send me an email or whatever you want to do.